Thanks, Tony, and thanks for inviting me to speak here. So yeah, as Tony said, I'm going to be talking about the tree evaluation problem. This is joint work with Ian Mertz that we're scheduled to present at Stock this year in whatever form that might take. So the talk's going to have two parts. So first I'll talk about the tree evaluation problem and why we care about it. And then I'll talk about a new algorithm we found that makes use of an idea of borrowed memory, and I'll explain later what that means. Okay, so the first part is actually based on a bunch of old work, which is mostly by people other than myself. So based on a couple of 2010 papers. I'm going to start by defining the problem after I give you a little bit of motivation for why it matters. Then I'll talk about a couple of abstractions called Pebbling games and branching programs, which we use to analyze the problem. And then before I move into the new algorithm, I'll talk about a couple of lower bounds that we had to work around in order to develop the new algorithm. So the motivation is separating complexity classes. So here's a chain of complexity classes. Don't worry too much if you don't know what all of these are. On the right side, we have NP followed by the whole polynomial hierarchy. And on the left-hand side, we have this weird class called uniform AC0 of 6. Now, as far as we know, AC0 of 6 is a really weak complexity class. For example, if you're trying to solve the problem where your input is a string of bits and you just want to know, are the majority of the bits 0 or 1? We don't know how to do that in AC0 of 6. And in between these two extremes, we have a whole range of different classes, which as far as we know, are all distinct from each other. But the embarrassing thing is that we actually don't know how to prove that all of these are not the same as each other. So any kind of separation on this line would be a breakthrough result. So today I'm going to be focused on two of these classes, log space and polynomial time. So the tree evaluation problem was introduced as an effort to separate these two. So to make sure everyone's on the same page, P stands for polynomial time. It's the class of decision problems which you can solve with a Turing machine, where the total number of steps it runs for is a polynomial in n, where n is the size of the input to the problem measured in bits. L stands for logarithmic space, and here the constraint is that the Turing machine can use at most order of log n memory. So if the Turing machine uses that much memory, then the total number of configurations the machine can be in is at most 2 to the order log n, or in other words, a polynomial in n. And assuming that the Turing machine eventually halts, it can't ever repeat any one of those configurations, so it actually can only run for a polynomial number of steps. So that means L is a subset of P, and the goal of the tree evaluation problem program is to show that that inclusion is strict. So it's not hard to show that the problem can be solved in polynomial time, but if you kind of take a stab at it, you get some intuition pretty quickly that you probably can't solve it in log space. And so the goal is to actually prove that fact, which would give us a separation. Okay, so now I want to talk about what the problem actually is. So the input to the tree evaluation problem is a complete binary tree with some information attached to every node. So the leaves of the tree just have a number attached to each of them, in this case 3, 1, 2, and 2. And the internal nodes, each internal node has a whole table of numbers. And we can use this input to recursively define a value at each node. So the value at a leaf node is just directly given as part of the input. And to compute the value of an internal node, you need to first compute the values, or you need to first know the values of its two children. And those two children values tell you where in the table to look. So for example, the left child of the root, its children are 3 and 1. So that means we should look at row 3, column 1, and we find the value 2. Similarly, the right child of the root, the children tell us to look at row 2, column 2. We find the value 3. And now for the root, we know that its two children's values are 2 and 3. So we look up entry 2, 3 in the table, and we find 2. And the value at the root is the final answer for the final output for tree evaluation. Or if you want to study a decision version of this problem, you can say the final output is true if that root value is equal to some special value, like 1. So this problem has 2 parameters. There's the height of the tree, which is 3 in this case. And there's also an alphabet size k, and that's also 3 in this case, which means every number that appears on the tree is between 1 and 3. And it also means that the numbers that appear, the tables that appear on the internal nodes are all 3 by 3. So given these parameters, the total size to encode the input, n, is equal to the order of 2 to the h internal nodes times k squared numbers that we're storing at each internal node times log k bits to store each of those numbers. And the leaves don't factor in here because they're dominated by that. Okay, so that's the problem. Now I want to talk about algorithms for solving the problem. So I'll introduce a computational model called branching programs, which we use to study it. And I'll also talk about an abstraction called Pebbling games, which is useful both for getting upper and lower bounds. So to understand a branching program, here's the input to the problem again. I'm going to say a query is any piece of that input that we might want to read. So a query can either be a leaf node, or it can be a cell, a specific cell in one of the internal nodes of, in one of the tables of any internal node. So a branching program is a directed graph where the nodes in the graph are called states. And each state is labeled by one of these queries, and the edges are labeled according to what the possible answers to that query might be. So to be a bit more precise, a branching program has 2 kinds of states. It has query states, which are labeled by these queries. Once you arrive at one of those query states, you follow one of the edges coming out of it, depending on the answer to that query. And you also have final states. Once the computation reaches a final state, that means you stop and you output whatever that state was labeled with. And finally, one of the states is labeled as the starting state, where you start. So let's see an example of a branching program for solving the tree evaluation problem. So just to make sure it all fits in one slide, I'm going to use a really small instance. I'm going to have a height 2 tree, and I'm also going to have an alphabet size of 2. So that means that there are only 6 possible queries. There are 4 different entries in the table of the root node that you can read, and then there are also 2 leaves, B and C. So here's a branching program that solves this instance of the tree, this size of tree evaluation problem. So notice, first of all, the states are arranged into layers going from left to right, starting with the starting state and ending with output. All of the branching programs that I'm going to talk about today are going to be arranged in layers like this. So the first state in our branching program queries the first leaf, B, and depending on the output, we go to one of the states in the next layer, which will then query the leaf C. Depending on the output of that, we end up in one of 4 states in the third layer, and each of these 4 states queries a different cell of the table of the root node. And finally, based on the result of that query, we end up outputting either 1 or 2. So let's pick an example input to the problem, and let's watch what our branching program does on that input. So we start at B. The value of the leaf B is 2, and the value of the leaf C is also 2, so we follow those 2 edges. we end up at the state in the third layer that queries the cell A22. We find the number 1 in that cell, and that means that we output 1 as our final answer. So one thing I want you to notice about this branching program is that the information that's remembered at each layer of it is different. So in particular, once we get to the second layer, we're remembering what the value of B is from the previous layer. And when we get to the third layer, we're remembering what the values of both B and C are. And the number of states in a layer will grow depending on the number of things we're trying to remember, because we need to have a separate state for every possible combination of those things we're remembering. So all of the lower bounds we have so far for tree evaluation problem depend on making some kind of argument that the branching program needs to remember some information at some point. So next I'm going to introduce Pebbling games, which are a useful abstraction for reasoning about what this program might be remembering at any given point in time. So Pebbling games were first introduced by Paterson and Hewitt in 1970. And in the case of the tree evaluation problem, it works like this. We have some complete binary tree of some height h. Let's say height is 3 in this case. And we have a limited supply of pebbles. And let's say we also have 3 pebbles. So these pebbles, they just start out in your hand. And then you're allowed to do 2 kinds of move. So the first kind of move is you can move a pebble to a leaf node of the tree. And then if you've put pebbles on both of the children of some internal node, then you're allowed to move a pebble to that internal node. And finally, the goal is to put a pebble on the root node of the tree. Okay, so let's try this. We have 3 pebbles to start with. So I'm going to start by putting 2 of the pebbles on the leftmost 2 leaves. Now the left child of the root has both of its children have pebbles on them, so we're allowed to move a pebble there. And this is good progress, right? So our goal is to put a pebble on the root, and we've already managed to put a pebble on one of its 2 children. So let's move on to the right side of the tree. So I'm going to put 2 pebbles on the rightmost 2 leaves, and now we're ready to put a pebble on the right child of the root, and we have an important decision to make. The decision is, which of our 3 pebbles should we move to the right child of the root? And well, the answer is basically just make sure you don't take this pebble that's on the left child of the root. Don't move that one over, because if we do that, we'll have lost all of our progress on the left side of the tree. So we can move either of the other 2 pebbles. And finally, the root node has pebbles on both of its children. And so we can go ahead and put a pebble on the root node, and we're done. So the important question here is, how many pebbles did we need in order to win at this game? In this case, we had 3 pebbles, and that was enough. It turns out that in general, for a height h tree, h pebbles will be enough to get a pebble on the root node. You can follow a simple recursive strategy to do that. And the number of steps you'll need to do that is 2 to the h minus 1, because that's the number of nodes in the tree. And this strategy basically visits every single node exactly once. So this theorem gives us a corollary about the tree evaluation problem, which is that you can solve the tree evaluation problem using a branching program. So the strategy turns into a branching program like this. Every step of the game turns into a new layer of the program. And the positions of the pebbles at any point in the game tell us what that layer is remembering. So the 2 kinds of move for the game correspond to things we are allowed to do in a branching program. So the leaves are directly available as part of the input, so it's no problem to directly load in the value of a leaf into our memory by storing that in one of the layers. And if we remember the value of in internal node's 2 children, that directly tells us which cell of that internal node's table we need to read. So we have an analogy to that second kind of pebbling move as well. So once we do that translation, since we're using at most h pebbles at a time, that means that we're remembering at most h values at once. And so the width, in other words, the number of states in any layer, is at most k to the power h. And the total number of layers is 2 to the power h, so we have 2 to the h times k to the h states. So it turns out this theorem about pebbling games is tight. So if you have only h minus 1 pebbles, there is no strategy that will put a pebble on the root node. The proof of this is a little bit less obvious than the first theorem. The first theorem, it's a simple recursive algorithm. This one is kind of an interesting argument. I'll leave that as an exercise. But it would be really nice if we could come up with a corresponding corollary for this lower bound. So it would be nice if we could say that any branching program at some point needs to remember h different values of nodes in the tree. So that would give us a lower bound of k to the h states. And for a long time, we couldn't come up with any algorithms that did any better than the pebbling game, than the pebbling algorithm. There were a few different ways you can approach the problem that look a little bit different from each other, but in the end, they all ended up using k to the h states. So this conjecture seemed pretty plausible. So this new algorithm I'm going to talk about is the first counterexample. Okay, so I promised you I would talk about lower bounds a little bit. So in order to talk about lower bounds, I first want to go in a little bit to talk about what it would mean for tree evaluation to be in log space. So to talk about what that means, we need to take the log of the input size. So the input size, as we saw before, is 2 to the h times k squared log k. That means that a log space Turing machine is allowed to use on the order of h plus log k memory. Now, if you could solve tree evaluation problem in log space, then you could convert it to a branching program, or a family of branching programs. And the idea for this conversion is that every distinct configuration of the Turing machine turns into a distinct state in your branching program. Now, the Turing machine can be in any of 2 to the order of h plus log k distinct configurations, which is the same as 2 to the order h times the polynomial in k. So that is our limit on the number of states. So in the other direction, if we can prove that no branching program can be made with that many states, that would prove that TEP is not in L. So let's look at the pebbling game in this context. The pebbling algorithm has a branching program with 2 to the h layers. The number of states in each layer varies up to k to the power h, and if you do some careful arithmetic, you'll find that the total number of states, if you add them up, is on the order of k plus 1 to the power h. So k to the power h is more than k to a constant. So this pebbling algorithm is effectively not a log space algorithm. The new algorithm I'm going to present uses k over h plus 1 to the order h times a polynomial in k states. So it turns out that when the height of the tree is reasonably large compared to k, specifically if it's at least k to the power a little bit more than 4/5, then this does better than the pebbling algorithm. But this is not a log space algorithm either, because we still have this power of k to the h, effectively. So neither of these algorithms rule out the possibility that maybe we'll be able to prove that tree evaluation problem is not in log space. But the existence of this new algorithm does at least tell us that if we want to prove this, doing it by arguments about pebbling strategies is not going to be the right approach. Okay, so I've talked enough about this mysterious new algorithm. Maybe I should begin to tell you how the algorithm actually works. Oh, sorry, I'm not there yet. Before I do that, I will get there very soon. I want to talk about a couple of the lower bounds we do have. So it turns out you can prove that solving this problem requires...
James, can you show the previous slide?
Sure.
So in particular, if, I mean, I guess normal parameters people use is k equal h equal log n, right?
So k equals h equals log n. I don't know if there's really a setting of normal parameters. Certainly we were normally thinking of k as being somewhat larger than h in a normal setting. Yeah, I don't know if we have any notion of what a normal...
But even k equal h equal log n was giving something like super polynomial. So in this setting, you get a polynomial upper bound.
Yeah, that's
yeah. Okay, that's good. Just to make sure I understood the parameters of the upper bound.
Yeah, you're not going to
cool.
be h is like log n, of course, but and k can be anything from n on down, but it's still very interesting when h equals k.
Yeah. Okay.
Okay, so it turns out that we can actually get a lower bound of on the order of k to the h states, just like the Pebbling algorithm, if you put some restrictions on the branching program that sound pretty reasonable. So in particular, if you assume that the branching program is read once, meaning that it's never, once it reads a piece of the input, it's never allowed to go back and read that same piece again. That gives us the lower bound. Also, if you assume that the algorithm is thrifty, that gives us a lower bound. So thrifty means that it never reads a piece of the input that doesn't matter. So in this example, our node's 2 children are equal to 3 and 2. That means that the only entry in the node's table that matters is the entry at row 3, column 2. So a thrifty algorithm is never allowed to even look at any of the other cells in this table. So our new algorithm beats this lower bound. So from this, we can infer that the algorithm doesn't meet either of these restrictions. So it actually violates them pretty strongly. The algorithm reads every single part of the input, so it's not thrifty, and it reads all of these parts several times over, so it's not a read once algorithm. Okay, so now let's move on toward talking about the new algorithm. So first of all, I'm going to talk about a few results related to reversible computation that kind of feed into it. And then I'll talk about how we use these techniques to build an algorithm for TEP. And I want to start with a paper that kind of caught our attention and showed us that we should be paying attention to reversible computation. So this paper is from 2014, and the title is Computing with a Full Memory, Catalytic Space. And it talks about this really weird model of computation. So here we're given a small amount of ordinary memory, and then we're given a large amount of extra memory. And the catch with the extra memory is that it's going to start out in some arbitrary state, and then once our computation's finished, we need to return the extra memory back to where it started. So it's sort of like your friend has lent you a hard disk. They lent you the hard disk already filled with data, and they said, you can use this hard disk however you like, but I need it back tomorrow. And once I get it back, it better have exactly the same data on it that it started out with. So at first sight, intuition might tell us that this extra memory can't possibly be useful. So for example, if you tried to use some particular piece of the extra memory, before you overwrite that memory, you'd better save a copy of whatever was stored there somewhere else, so that once you're finished with your computation, you can copy it back. So it's hard to see how you could get any net gain from the extra memory. But surprisingly, they showed that it seems like you actually do get a benefit. So in particular, with only a logarithmic amount of ordinary memory and a polynomial amount of this borrowed extra memory, you can compute things that we don't otherwise know to be in log space. For example, the determinant of a matrix or anything that's in non-deterministic log space. So this caught our attention because it rules out one of the approaches we were trying to follow to get a lower bound for tree evaluation problem. So our argument went something like this. So if you want to compute the value of the root node A, then at some point, you need to compute the value of its left child B. And then you need to remember the value of that left child B, keep that in memory while you're computing the value of C, so that once you're done computing C, you'll have both of the values. So that means you need to use log k bits of memory to remember B while you're recursively continuing your computation. So the argument goes, since you have h levels in the tree, that means you need to store at least h log k bits of memory overall. So this catalytic result basically means that this sort of argument is never going to work. So even if we could somehow argue that our program at some point needs to compute the value of node B and remember it, this result says that while we're doing the computation for C and keeping that value in memory, the computation for C can borrow that memory, those log k bits, and make use of them, even though it has to restore them to their original state once it's done. The techniques that are used in this catalytic space paper actually go back pretty far. So there's a paper in 1989 by Barrington, which shows that with branching programs limited to have a width of only 5 states in each layer, you can do quite a bit. And then there's a paper by Ben-Orr and Cleve in 1992 that says you can do quite a lot of arithmetic with computations that only remember 3 numbers at once. So what both of these papers have in common, one thing they have in common is that they show you how to trade off time and space in order to get algorithms that use an extremely limited amount of memory. And another thing that they have in common is that they both make use of an idea of reversible computations. So for our algorithm, we're going to use a concept of reversible computations that operate on registers. So our model is that we'll have n inputs, x1 through xn, that we can read, and we'll have m work registers, r1 through rm, and all of these will be elements of some ring R. And we're interested in reversible instructions. So for example, an instruction could be, we take register 4 times input 1, and we add that to register 5. And the inverse of that instruction can be done by just subtracting instead of adding. If you run both of these instructions in sequence, the effect is as if you did nothing at all. So since we're interested in computations where your extra memory starts in an arbitrary state, I'm going to introduce some notation for the initial state. So we're going to say tau sub j denotes the starting value of register rj before the computation runs. So in this setting, let's imagine we want to compute some function f. So I'm going to say a sequence of reversible instructions cleanly computes f into register I if at the end of the sequence of instructions, the final value of register I is its initial value plus the value of f. And the word clean means that at the end of the computation, all of the other registers should be unchanged. So one thing to keep in mind is the computation is allowed to use those other registers. It's allowed to write to them, but it just needs to make sure that any changes it makes get undone before the algorithm finishes.
Can I ask a question?
Yeah.
Yeah. So in the can you get back to the previous slide, to the catalytic? Yeah. So everything in NL is can be done by a catalytic algorithm.
Yeah.
And one thing you didn't talk about is that tree evaluation is in NL. Is it?
No, so actually there is also a separate effort, or people who are trying to prove lower bounds for tree evaluation problem are also working on the non-deterministic version. And the last I heard is that they still are trying to prove that lower bound to show that it's not in NL.
It's not known to be in NL. Can't you guess the sequence of contents? I mean, by a branching program, can't you guess the sequence of table entries you need to look at in order to figure out the output?
So you can make guesses like that. The trouble is that you need to remember what guesses you made and verify them later after you're done your computation.
So in other words, there's no black and white pebbling.
Exactly.
Even black and white, we don't know an upper bound.
Yeah, in fact, we have lower bounds for black and white pebbling strategies.
Which are?
I don't remember exactly. I think they look something like k to the h over 2, k to some constant times h.
Yeah, you save that's exactly right. That's the upper and the lower bound for black white.
I see. Okay, that's good. That's helpful. Yeah, thanks.
Okay, cool. So we were looking at this notion of clean computation, where at the end of the computation, the final value of register I should be equal to its initial value plus the function f that we're trying to compute, and the computation restores all the other registers. And if that computation is made out of all reversible instructions, which is always going to be the case for this talk, then we can invert that entire sequence. We invert it by running the inverse of each instruction and running those instructions in reverse order. And it turns out if you do that, you end up with a clean computation for negative f instead of f. So we like this definition for two reasons. The first reason is that this notion of clean computation makes it easy to design algorithms that are able to make use of borrowed memory. And I'll show you what I mean by that later. The other reason we like this model is that we can convert any sequence of reversible instructions into a branching program. So I've moved our definition of clean computation to the top of this slide, and I've added a lemma, which is that if we have any sequence of L instructions that cleanly computes some function f, and each of our instructions has a certain form, then we can make a branching program. So the form of the instructions is actually pretty general. The instructions allowed to update all of the registers at once according to any function g, just so long as that function g only depends on one input. And that restriction comes from the fact that a state in a branching program is only allowed to query one single piece of the input. So if we have this sequence of instructions, we end up with a branching program using L times the size of the ring to the power m states. And the way that works is that each of the L instructions turns into a layer in the branching program. Each layer is going to remember the values stored in all of the registers. So there are size of the ring to the power m possible configurations that those m registers can be in. So our overall strategy is going to be this. We're going to try to make a clean computation for solving the tree evaluation problem. And then we're going to apply this lemma to say that that means that there's a branching program. So let's look at a couple of examples of clean computations. So for example, suppose we want to cleanly compute input 1 plus input 2 into register 1. So the program's pretty simple. We just add x1 to register 1, then we add x2 to register 1. So after we run the first instruction, register 1's value is its original value tau1 plus x1. And after the second instruction, its value is tau1 plus x1 plus x2. And so that means we have cleanly computed x1 plus x2. So our next example is a little bit more complicated than this. We're going to try to combine programs to compute the product of their outputs. So suppose we have a sequence of instructions P1, which cleanly computes a function F1 into register 1. And we also have a sequence of instructions P2, which cleanly computes another function. So this lemma is going to tell us that we can cleanly compute the product F1 times 2 into a third register R3. And we do it with a program that looks like this. This program is made out of, you can think of it as being made out of two interlocking parts. So the first part is that we're running the subroutines P1 and P2. So we run P1 forward, then we run P2 forward, and then since we are able to run invert programs, we're able to then run P1 backward, and then we can run P2 backward. And the other interlocking part is that in between these subroutine calls, we're going to be adding and subtracting R1 times R2 from register 3. And because these subroutines are modifying registers 1 and 2, the effect of these instructions is going to be different every time. So let's run through this and see what the overall effect is. So after we run the first instruction, well, everything started out at its initial value. So the new value for register 3 is tau3 plus the initial value of register 1 times the initial value of register 2. So then we run our first subroutine. That has the effect of updating register 1 to have the value tau1 plus f1. And then when we add r1 times r2, we'll cancel out that tau1 times tau2 term from the first step. And sorry, we're subtracting r1 times r2. So we'll cancel out that tau1 times tau2, and we'll also get an extra term of f1 times tau2. So now we run the other program. Once we've done that, register 2 has value tau2 plus f2. So both registers have their functions added to them. And once we add register 1 times register 2, we will cancel out that f1 times tau2 we had from the previous step, but we add a bunch of stuff to replace it. So we add back tau1 times tau2. We also add this annoying term tau1 times f2, but we also managed to add f1 times f2. So if you remember what we're trying to do here, f1 times f2 is what we're trying to compute in the end. So the only thing we have left to do at this point is clean up. We have to get rid of those extra terms like tau1 times tau2 that we don't want to be there. So we run program 1 backward. That restores register 1 to its initial value tau1. Then we subtract r1 times r2, and that has the effect of canceling out exactly those terms that we didn't want. So now register 3 has value tau3 plus f1 times f2. And the very last step is just one more bit of cleanup. We restore register 2 to its initial value. So now everything's back to its starting value, except that register 3 has f1 times f2 added to it. So that means we're done.
Question.
Yeah.
Is it different than the way that Benor and Cleve implement their multiplication when they do when they use 3 registers?
It's closely related. They have a slightly different induction hypothesis where they're saying you should be able to add some register times f1 times f2. So it's not exactly the same thing, but it's definitely very closely related.
Okay.
So for any of these lemmas, the important thing that you want to understand is what did it cost you to do this multiplication? So in this case, we had to do 4 subroutine calls, and I think it's the same in Benor and Cleve that they have to run each of the subroutines twice.
Yeah.
So we had
the same. Yeah.
Yeah, they don't have these intermediate instructions. It's just for recursive calls, but they also have relabeling of the registers and everything.
Okay, so this cost us 4 recursive calls. So that's kind of expensive, but on the other hand, this is very efficient with memory. So one thing I want to point out, and this is of course the same with any of these other techniques involving reversible computation, is that the subroutines P1 and P2 are able to make full use of all of the registers. So we don't need to reserve any memory for this top level routine. So in particular, P1, for example, is designed to work for any initial values of registers R1, R2, and R3. And since P1 is a reversible computation, it's designed to restore all of the registers back to their original values, except for the output register. So these subroutines can just make use of the same 3 registers, and if they in turn call other subroutines, they can also make use of exactly the same 3 registers. So we don't end up with any extra memory needing to be reserved for each recursive layer of our program. Okay, so I've talked a little bit about some techniques for reversible computation, so now I want to talk about how to apply them for tree evaluation problem. It's generally easier to apply these techniques if we can think of things in terms of algebraic formulas. So the next thing I want to do is to come up with a formula for the value of the root of the tree in terms of the values of its 2 children. So from here on out, I'm going to work over the ring with just 2 elements. So integers mod 2, 0 and 1. And I'm going to define the indicator, brackets x equals y, to be equal to 1 if x equals y and otherwise 0. So now suppose we have this table in our root node, and we're trying to come up with a formula that tells us whether the root node is equal to 1. So the indicator v equals 1, where v is the root node. So to build this formula, the first step is to look at all the places where 1 appears in that table, since these are the only ways that the root node can have that value. Each of these places where 1 appears is going to turn into a term in our formula. So the first term in our formula says that L is equal to 2 and R is equal to 1. Second term says L and R are both equal to 2, and the third term says L equals 1 and R equals 3, identifying the 3 possible places in the table. So here's the general formula. So let's say F sub v denotes the values in the table. So to build the formula in general, we can take a sum over all of the entries, y, z. In each case, we'll add this indicator that checks whether the value of the y zth entry is equal to our target x. And then we multiply that by the indicators for the left child being equal to y and the right child being equal to z. So this gives us a formula for computing whether or not the root value is equal to x. So the next step is to try to turn this into an algorithm. So I'll put that formula at the top of the slide for reference. So I'm going to call this algorithm check node because it's checking whether node v is equal to x. The algorithm has three parameters. There's the node that we're trying to compute. There's the target value x that we're checking against. And then there's some register I that we should put our output in. So the goal of this algorithm is to flip the bit stored in register I if and only if the value of node v is x. So here's how it works. If v is a leaf node, then the value of v is just part of the input directly. So we can just implement this as one single instruction. Otherwise, if it's an internal node, then we're going to implement that formula on the top of the slide. So we're going to loop through all of the values y and z that go into the sum. And in each case, we're going to add the value of that indicator saying the yz entry is equal to x times the indicators for the two children. So there are three terms in this product. So the first term, we don't really have to worry about too much. The indicator for that entry in the table is just directly part of the input. So effectively, we've just got a product of two things to worry about. To find the product of those two things, we can make use of that multiplication lemma we just saw. So we're going to allocate two other registers, other than register I, call those registers j and j prime, and we're going to use 4 recursive calls to check node on the two children in order to implement that multiplication. And so that completes the algorithm. And the question to ask about it is, how big is the branching program that we get if we implement this algorithm? So the algorithm uses 3 registers. As I mentioned earlier, we're allowed to reuse registers. So the recursive calls can just use those same 3 registers over again. The total program overall just needs 3. Each register is 1 bit. So that means the width of our branching program is 8, just to store the 8 possible values for 3 1-bit registers. Now the length of the branching program, oh, I forgot to update. Okay, so the length of the branching program depends on the number of recursive calls we're making at each level. So at each level, we're making 4 times k squared recursive calls. So that means over the h minus 1 levels of recursive calls we're going to do, we end up with a length of 4k squared times h minus 1. So there's a small error on the slide. So 4k squared times h minus 1 is actually pretty bad. If we look at the Pebbling algorithm, as a reminder, that algorithm just uses basically on the order of k to the h states. So somehow we've managed to do worse than Pebbling. Okay, so we're going to need some more tricks if we're going to make this algorithm useful. So in order to see what we should try to do next, let's dig a little bit into this for loop that the algorithm runs. So the algorithm loops over all pairs y and z, and in each case, the algorithm invokes this multiplication lemma. So let's take a look at how that lemma works. If you remember, the algorithm implementing the lemma looks a little bit like this. So we have 4 calls to the subroutine, which I've marked in blue on this slide. And then in between those 4 calls, we have these manipulations that add or subtract the other 2 registers. And this is put in a for loop, which basically means we repeat a similar sequence of instructions over and over again. So the observation here is it would be really nice if we could parallelize this so that we don't need to make quite so many subroutine calls. And it turns out that you can actually make a parallel version of this if you do a trick of computing all of these indicators at once, so instead of just having the subroutine compute the indicator, for example, for left child equals 1, we're going to make the subroutine in parallel compute the indicators for left child equals 1, left child equals 2, left child equals 3, and so on. And if you do that, you can collapse this whole algorithm so it actually just has one column. So in order to do that, we're going to think of vector registers that are storing not just one bit, but k bits, where a bit is 0 if the value of the node is not equal to that index and it's 1 otherwise. So we call this the one-hot encoding. So given a value x, the one-hot encoding just has a single bit of 1 in the appropriate index. For example, when k equals 3, the one-hot encoding of the value 2 is just 0, 1, 0. So let's see how we can make an algorithm to do this all in parallel. So I'm going to call this compute one-hot, and it's going to use vector registers where each register uses k bits. The parameters of our algorithm will be a node v and some target register I, and the goal is to add the one-hot encoding of v to the vector register I. So effectively what that means is we just want to update a single bit of the register I, where the index of the bit depends on the value of v. So let's see how to implement this. So first of all, if v is a leaf node, then all of the information we need to perform this operation is available in one single piece of the input. So that means that this whole thing can actually just be implemented in one instruction, just like in the previous algorithm. Otherwise, for an internal node, we're going to implement our multiplication algorithm. And I've sort of written out that multiplication algorithm again here, where again I've highlighted the recursive calls in blue. So our recursive calls are querying the one-hot encoding for the children L and R, and we can do that using recursive calls to compute one-hot. In the original multiplication algorithm, we interleave this with steps that add and subtract rj times rj prime. In this case, instead, we're going to add and subtract some function f of the two vector registers. And the trick is just in getting the right function f. So it turns out that the right thing to do, if you want to design this function, is this. So we'll start with the original formula for the root value, which I put at the bottom of the slide there. And then to compute bit number x of this register, so I'm giving you a formula for bit x of this function f, all you have to do is take that formula at the bottom, and where you see the indicator left child equals y, you instead substitute in the value of the yth bit of register j, and where you see you should be checking the indicator right child equals z, you just substitute in the zth bit of the register rj prime. And so effectively what this algorithm ends up doing is doing all of these multiplications in parallel. So let's see what this gives us. It gives us a branching program where the width, well, we have 3 registers still, but each register takes k bits. So our width is now 2 to the power 3k. On the other hand, we've reduced the number of recursive calls. At each level of the recursion, we only have 4 recursive calls. And we also do on the order of k squared work at each step. So that works out to a total of order of k squared times 4 to the h layers. And if you multiply those two things together, the number of states is 2 to the order k plus h. Okay, so let's compare. Pebbling algorithm is k plus 1 to the h, and our new algorithm is 2 to the order of k plus h. So in order to compare these two, let's rewrite the Pebbling algorithm as using 2 to the power h times log of k plus 1. So now that means the one-hot algorithm is better when h times log of k plus 1 grows faster than k plus h. So that's the same thing as when the height of the tree h grows much faster than k over log k. Okay, so we've beaten the Pebbling algorithm in some settings. So the obvious next step is, can we do better than this? And I guess I've only got 4 minutes left, so I'm guessing I should probably try to wrap up soon.
You can take 5 extra minutes. It's okay.
Okay, sure. So yeah, I'll try to just do the rest fairly briefly. So it turns out, yes, you can do better than this algorithm. You can kind of extend the range of parameters for which we beat Pebbling. And the basic idea behind that is that our one-hot encoding is extremely inefficient. Using k separate bits just to store a value from 1 to k is kind of terrible when, in theory, we could store that value using just log k bits. The trouble with using an encoding with log k bits is that our formula then is going to have to be a higher degree polynomial. So we'll end up with a polynomial with degree 2 log k. We end up with having to do a multiplication algorithm where the number of recursive calls is exponential in the size of the encoding. So if we have log k bits, then the number of recursive calls is actually going to be k squared, actually, 2k squared. So if we try to apply this blindly, I'll just skip to the number of states. This binary encoding gives us a branching program with on the order of k to the 2h states. And again, this is just worse than our Pebbling algorithm. But the key trick is to interpolate between the two encodings. So our original encoding was this extremely inefficient one-hot encoding, where we have k bits and we set one of them to be 1. And the advantage of that encoding was that our polynomial just has degree 2, which means our multiplication lemma only needs 4 recursive calls. And the other extreme is this binary algorithm with an extremely efficient encoding, but where working with the encoding requires very high degree multiplications. So the trick is to come up with a hybrid algorithm that interpolates between the two. So we come up with an encoding which has a parameter a, where if you set this parameter a to be 1, you end up with a one-hot algorithm. You set parameter a to be log of k plus 1, and then you end up with the algorithm that uses the binary encoding. And the trick is, if you set a to be just the right value, you end up with an algorithm, if you look in the bottom right corner of this table, that uses a total number of states of k over h plus 1 to the power of 5h times some polynomial. So that means our hybrid algorithm is better than the Pebbling algorithm just as long as h grows faster than k to the power of 4/5. Okay, so that's the basic upshot. We use these techniques and then we interpolate between them to get just the right setting of parameters. Maybe what I'll do is just give you a brief taste of, I think I should just skip ahead to future work. So there are basically 2 directions to go from here that present themselves. The first one is to try to get a better algorithm. So the main bottleneck in these algorithms seems to be these products, where computing a D-array product requires an exponential number of recursive calls. So it would be nice to have some technique to do better than that. And we're not the first people to observe that this would be a nice thing to have. Another interesting direction would be lower bounds for tree evaluation problem. So as I mentioned earlier, we have some lower bounds for tree evaluation problem, but this new algorithm kind of flaunts those lower bounds because it doesn't follow the rules. It's not a read once algorithm and it's not a thrifty algorithm. So it would be nice to come up with new kinds of lower bounds where even if they don't necessarily yet apply to all branching programs, at least maybe extend them so that this kind of algorithm is covered by them. Okay, so that's everything I wanted to talk about. Thank you.
Thank you very much. That was a very beautiful talk. Any questions from anyone?
Yeah. Can you use the same techniques for non-deterministic algorithms?
We haven't tried that. Ian, do you know if catalytic techniques or this kind of thing has been used for non-deterministic?
There's some literature on non-deterministic catalytic log space, for example. Although it should be said again, we're in a slightly different model than the catalytic one, since we're working with total low space. I think that, yeah, the simple answer is we haven't tried non-deterministic non-deterministic branching programs using these sorts of techniques. But it's I think I thought about this a little bit at one point, and it's not at all obvious. Like, you'd want to use it to well, yeah, it's not obvious how you would use the non-determinism, I guess.
Yeah, I mean, we're working with reversible instructions, so I'm not sure what it would mean to reverse a non-deterministic choice.
Yeah, that's a good point. The non-determinism, yeah, you'd have to be able to guess it in reverse if it's in a reversible instruction.
I guess the SL model symmetric log space is reversible, right? And it's sort of a reversible non-deterministic type algorithms.
Good to know.
I had a different question. Given your algorithm, do you now believe that this problem is in L or not?
I don't. I'll say I don't believe it yet. So
I believe it.
You believe it's an L? So okay, I don't know. I feel like when I try to come up with improvements to the algorithm, it still seems like I'm fighting pretty hard for even small improvements. So I would personally be a little bit surprised if you can solve it in log space, but it's hard to know.
Yeah, I think one thing that's worth noting is, if I can jump in, these d-ary products that James briefly mentioned. So currently, if you want to multiply d things together, you pay like 2 to the d in terms of how many recursive calls you do. Yeah, thanks. So if you can improve this down to polynomial in d, then you get like a log k to the h algorithm. And if you bring it down to a constant number, like with the binary case, then you actually do get you do get a log space algorithm. And we do have a way to do polynomial in k number of steps to do this d-ary multiplication. It just doesn't parallelize over this big sum. So there's reason to think that you could get a better product algorithm, which would get you a much, much better branching program approaching L.
Okay, maybe another question. So for general DAGs within degree 2, is there some parameter which is like the Pebbling number, which captures what your algorithm can do?
So you're saying try to use this algorithm to solve a Pebbling kind of problem, but on a DAG.
Yeah.
We haven't tried that. So the nature of the algorithm is it doesn't really have this notion of like reusing. Okay, so a DAG's going to have some nodes within degree 2, and I'm not sure how this algorithm would be able to reuse the computation for that, because you know, we come at the node 2 ways, and in each case we're kind of doing this reversible thing where we add the value of the node to some register. So it's not clear when you come around to the node from the other direction how you could make use of that a second time. So off the top of my head, I'm not sure how this would be useful for DAGs, but maybe there's some way we could do it.
Great. Yes, I agree. It was a really nice talk, James. Should we thank the speaker? Yeah.